Okay, so now what we want to do is start looking at integration, specifically evaluating a triple integral in spherical coordinates. So again, what we're trying to do is sort of look at what the analogy of a box would be in spherical coordinates. So what we're doing is we're going to look at intervals, or increments is another term for this, in each of our components, or each of our coordinates in spherical coordinates, rho, theta, and phi. So if I have an interval in rho, specifically if rho is between a and b, then that's giving me the set of all points that are between a and b units away from the origin. So that's going to give me the edges, these edges of this spherical wedge. That's what we call this thing here. If I look at an increment in my theta, that's going to, remember this is my change in theta down here. So we're looking at a change in our angle against the positive x-axis. That's going to create these edges of this box right here. And then finally, if I look at an increment in phi, that's changing the angle. So delta phi is what I'm going to call that increment. That's going to change the angle between each point and the positive z-axis. So if phi is between c and d, those are two angles, that's going to give me these edges. And you can see how each increment gives me the different edges of this box-like solid. And again, we call this type of a solid a spherical wedge. Now, just like we did with double integrals and taking rectangles and breaking them up into subrectangles, or rectangular boxes when we first talked about triple integrals in 15.6, breaking those up into sub boxes, I want to break this thing up into a bunch of sub-spherical wedges. And the idea is the same as it's been anytime we've started with a Riemann sum of some kind. We want to take each of these intervals and split them up into sub-intervals. So if I break this, and this into several sub-intervals, it's going to like dice this thing up into a bunch of little sub-boxes or sub-spherical wedges. And again, if I look at the ith interval for rho, jth interval for theta, kth interval for phi, that's going to single out one of those little sub-spherical wedges, which I'm going to call vijk. That's going to refer to the volume of that. It's actually, sorry, eijk is the sub-spherical box that I'm talking about. Delta V is going to refer to its volume. So we know that in order to use the Riemann sum to come up with an integral, we do need to know what the volume of one of those little spherical wedges would be. So let's imagine that this guy right here is the spherical wedge eijk. Okay, it came from one of a subinterval from each one of these. I want to come up with a volume for this. Now, it's an unusual solid, so we're going to start by looking at an approximation to it. For small values of delta phi, delta theta, and delta rho, this solid looks very, very close to a rectangular box. So if I try to imagine it as a rectangular box, then I need to know the length, width, and height of this thing. Multiply those three things together. So some of these edges are easier to find than others. For example, this edge right here, which let's call this the width, that's given by delta rho. So that's going to be one of the things I use in my multiplication here. Now, let's say I want one of these edges here. Okay, so that edge is created by this change in theta down here. Okay, and it's a little difficult to picture, but this edge is curved, you notice, and really what it is, it's an arc in a circle. So imagine for a second that we were to find the length of this arc of this circle right here. We need a formula for that. Now, I didn't write this down here. I'm going to write it up above. This is something we learn in trigonometry. The arc length of an arc in a circle subtended by an angle theta, if theta is given in radians, is r theta, radius times the angle itself. Okay, so that's what we're actually seeing down here. Ri is going to correspond to this length down here. That can be considered the radius of a large circle here. The angle between them is what we're calling delta theta. Now Ri, on the previous video, we gave a conversion formula for R. It was equal to rho sine of phi. In this case, everything's being indexed by these i's, j's, and k's. So really, in our case, that would look like phi I sine of, I keep mixing up my phi's and my rho's. Rho I sine of phi k, and then the angle is delta theta. So this would represent the length of this arc right here, but that arc is going to be swung upwards and become the arc that we see here, or the arc that we see here. So that is going to represent what I'm going to call, let's just say, the length of this box. And you're seeing that element show up here. Finally, we need this edge right here, but this is another arc of a circle. This arc is subtended by the angle delta phi. So r times delta phi. R, remember, means radius in this formula, and the radius this time is not the same thing as the Ri that we see down here. It's rho I. That's the distance between the origin and this point. If we treat that like a line segment and we swing it this way, we trace out this arc of that circle. And the length of that arc would be rho I times delta phi. So we're seeing that here as well. If we treat those like three straight edges that create a rectangular box, then the volume of that rectangular box would be the product of those three, which, after multiplying everything down, comes out to this expression right here, rho I squared sine phi k times delta, a change in each one of our coordinates there. Now this is an approximation because this is not actually a rectangular box. It's got curved edges, but we can make an argument, and we're not going to do this here, but there is an exercise in the book, I believe it's problem 49, where you can prove this. You can use the mean value theorem to show that there actually exists a point contained in this spherical wedge with these coordinates, where if I substituted these in for the phi I and the rho I and the phi k here, the volume will be exact. So we can kind of invoke the mean value theorem to turn this approximation into an exact volume, but we're going to skip the details here. So how do we create an integral out of this? Well, what I'm going to do is say that this xij k star, yij k star, zij k star, let's suppose that these are the rectangular coordinates for this point in spherical coordinates that I'm referring to here. What I want to do is work with the definition of the integral as a Riemann sum. So we know that the triple integral of f of x, y, z dv over e is given by this triple sum, limit as L, m, n goes to infinity of this triple sum of this point right here. Remember, this point has to be some point that's within this volume element here, in order for this to be a Riemann sum. But again, this argument says that this would be in that little spherical wedge, times delta v ijk. And then we make some conversions. So each one of these I convert into spherical coordinates, which is here. And here's kind of the key thing. Delta vij, that little volume element, becomes rho I squared sine of phi k, delta rho, delta theta, delta phi. This is similar to what happens in polar coordinates and spherical coordinates. When you make the conversion, your dA or your dV become r dr d theta, or r dr d, or dz dr d theta, or something like that. So instead of picking up a new factor of r, we're picking up a factor of rho sine of phi. So to summarize all this, this is what a triple integral in spherical coordinates will look like if we make a conversion. We pick up this extra factor right here of phi squared sine of sorry, rho, I don't know why I keep calling that phi. It's a rho squared sine of phi. So, and that's where the spherical wedge has this form. And we can do more general regions as well. Typically what we look at is where rho is bounded by two functions of theta and phi. But let's just jump into an example just to kind of start getting the hang of this. So we're being asked to evaluate a triple integral over the square root of x squared plus y squared plus z squared dv, where e lies above the cone, z equals the square root of x squared plus y squared, and between these two spheres, x squared plus y squared plus z squared equals 1, and another one where it equals 4. Okay, if you try using anything other than spherical coordinates for this problem, it's a beast. It's pretty bad. So let's start by sketching this region, and we'll see pretty quickly why spherical coordinates are way better for a problem like this. First of all, go like this. So we're going to try and sketch this solid, x, y, z. Now this is the top half of a cone because it's a positive radical instead of a negative. So we're looking at a cone kind of like this. Okay. Now these two spheres that are being described are both centered at the origin, and one has a radius of 1, the other is going to have a radius of 2. But if you think about it, we're only looking for the portions of those spheres that are above this cone. Another way of saying that is inside the cone. The sphere x squared plus y squared plus z squared equals 4 is going to have a radius of 2, and we're just going to get like the top little cap of it, because anything beyond that is going to be outside of that cone. You get something that looks almost like an ice cream cone. Then the one with a smaller radius, a radius of 1, is going to look similar, but it's going to be further down because of the smaller radius. So that's like the cap of that sphere. Okay, so the solid E is everything between these two little spherical caps within this cone. All right, now one other thing we need to, we're going to need in order to solve this problem is this angle right here. So if I were to look at the trace of this cone in the YZ plane, I would see that this edge right here, first of all, is going to be a line with a slope of 1. That's not hard to see. You can go straight to the equation and determine that. But if the slope is 1, that means the angle that this thing creates with the positive z-axis, which is phi, remember, is going to be pi over 4, 45 degrees. Okay? So the reason I'm doing that is because I need a description of this region in spherical coordinates. Let's attempt to get that down here. E equals the set of all rho, theta, phi, such that. Okay, so rho, if I take any point trapped within this cone and between these two spherical caps, it's always going to be within 1 to 2 units away from my origin, because that's the radii of either of these spheres. So rho is going to be between 1 and 2. It's the spheres that are giving us that. All right, theta. What can I say about theta? Well, if I pick any point in this solid here and rotate it anywhere I want, if I rotate it a complete 360 degrees, it's just going to create a circle that's still completely contained in that region. So there's really no restriction on theta. I'm just going to say theta is between 0 and 2 pi. Okay. Finally, I need a restriction on phi, and we started talking about that here. So if you take any point in this solid, then the line segment connecting that point to that point to the origin is going to have an angle phi somewhere between 0, that would put it on the positive z-axis, and pi over 4. Okay. So now comes the conversion into spherical coordinates. So we're looking at this triple integral here, x squared plus y squared plus c squared dv. okay? And again, as intimidating as this thing looks, really all this means is take your integrand and convert it into spherical coordinates. Well, fortunately, the x squared plus y squared plus z squared is described really conveniently as just rho squared. We had that as one of our conversion formulas. If I take the square root of that, it's just rho. So I know that my integrand is going to look like a rho with some extra stuff, which we'll get to, but let's also set up the iterated integral. Notice the order of integration that's happening here. D rho on the inside, d theta, and then d phi on the outside. So my limits on phi are going to go on the outside. 0 to pi over 4, then theta, 0 to 2 pi, then phi, 1 to 2. We said our integrand would change to rho, like this, but then again, remember, in the conversion of spherical coordinates, we pick up this extra factor of rho squared sine of phi. That means that the rho here will multiply to that and actually give me a rho cubed. Sine of phi, d rho, d theta, d phi. Okay. This is just a big product of functions of one coordinate or one variable at a time. So I can use that convenient property that lets me factor this out into 3 different integrals. Remember, d phi is the outer one. Let's take this all the way out. 0 to pi over 4. Sine of phi d phi. Integral from 0 to 2 pi d theta. And then I have integral from 0 to 2 of rho cubed d rho. Okay? From here, these are all single variable integrals. Each one of these is fairly straightforward to solve. We're going to get negative cosine of phi from 0 to pi over 4. We're going to get theta from 0 to 2 pi. We know that's just going to be 2 pi. And then we get rho to the 4th over 4 from 1 to 2. I'll skip the arithmetic because that's the easy part. Once you've plugged everything in and simplified it down, you should get something at least equivalent to this. 15 pi times 2 minus root 2 all over 4. Okay? That would have been way, way worse if we didn't convert to spherical coordinates, but with the conversion, it actually wasn't that bad. We'll look at one more example in the next video, and then we'll move on.